On August 6, 1945, Little Boy, nicknamed Little Boy, weighing 4 tons and carrying a 65-kilogram explosive charge, released 15,000 tons of TNT in an explosion over the city of Hiroshima. 3 days later, on the 9th Fat Man, nicknamed Fat Man, weighing 4.5 tons and with an explosive charge of 6.4 kg, released 21,000 tons of TNT in an explosion over the city of Nagasaki. 16 years later, on October 30th, 1961, the Tsar Bomba, weighing 27 tons, exploded over the archipelago in Novaya Zemlya, releasing 57 million tons of TNT, or 57 megatons, becoming the most powerful nuclear weapon ever made by man and the largest detonation ever carried out by humanity. Its destructive power is equivalent to all the explosives used in World War II multiplied by 10. On the outside of several nuclear bombs, we see these devices. Some may be at the front of the bomb, others on the side, as in the case of Little Boy. But what are these devices? To understand the function of these devices, we need to understand that nuclear bombs, like those used in Hiroshima and Nagasaki, were designed to explode in the air before hitting the ground, and not on impact, to maximize the weapon's destructive power. Nuclear bombs have 2 critical systems, the arming system and the detonation system. The arming system is the part of the bomb that generates the necessary signal to arm the bomb. This system ensures that the bomb does not accidentally explode while it is stored or being moved. The detonation system, on the other hand, is the part of the bomb that generates the signal for the detonation or explosion of the bomb. This system is composed of radio altimeters, batteries, fuses, sensors and barometric probes, timers, antennas, microcontrollers, contact fuses, proximity fuses, among others. And these devices belong to the bomb's detonation system. These devices are radio altimeter antennas, barometric probes and sensors, and based on the data provided by them, the bomb will be detonated. But how does that work? Depending on the power of the bomb, there is an ideal altitude for it to explode. After this altitude was carefully calculated by the scientists and engineers, this information was stored in the bomb's computers. As soon as the bomb was dropped and began its descent, the timers were started and the barometric probes measured the atmospheric pressure and compared it with the stored data. At the same time, the radio altimeters were responsible for determining whether the altitude for detonation had already been reached. As soon as the altitude was reached, these devices sent a signal and the bomb exploded. The detonation of Little Boy and Fat Man was carried out in 3 steps. In the first step, as soon as the bomb was dropped, timer clocks counted down 15 seconds, preventing the bomb from exploding in the initial moments of the fall. In the second step, barometric probe sensors measured the atmospheric pressure, preventing the bomb from exploding before reaching 7,000 feet or 2,000 meters. In the third step, just before impact, the radio altimeters measured the distance to the ground, and when the set altitude was reached, the bomb detonated, and even in several nuclear bombs, we see that they have this structure at the back, which can come in various shapes and sizes. In fact, non-nuclear bombs also have this structure. But what is this structure for? This structure is called a tail fin or tail stabilizer, and its function is to stabilize the bomb during its fall toward the ground. Not only to stabilize, but also to ensure that the right part is properly pointing toward the ground. Since atomic bombs use radio altimeters, which emit signals, and these signals are reflected from the ground, they can tell if they've reached the correct altitude by comparing the sent and received signals. For the explosion, the bomb needs to be in a stable fall so that these devices work properly and accurately. So, as soon as the bomb is dropped, these stabilizers Keep the bomb stable throughout the entire fall, and keep it in the correct position for the explosion, preventing it from spinning out of control. Atomic bombs are considered weapons of mass destruction with high incendiary power, high biological risk, and a high potential for contamination and pollution from radioactive waste and debris. So their designers must make sure that such a weapon never explodes accidentally due to high-speed impacts, accidental drops, fires, sudden movements, intense heat, intense cold, degradation caused by time, or corrosion. But how can the designers make atomic bombs immune to all these disaster situations that would likely cause the bomb to explode accidentally? Every new bomb built with a new design was subjected to a series of tests. These tests included placing the bomb in the middle of a pool filled with burning jet fuel, detonating explosives near the bomb to make sure that an accidental ignition wouldn't occur, dropping the bomb from different heights to ensure that, upon impact, the bomb would never explode, and subjecting it to high-speed impacts against concrete walls. All of this to make sure that under no circumstances would the bomb explode when it wasn't intended to. In 1917, in Halifax, Nova Scotia, a ship called Mont Blanc, loaded with explosives for World War I, collided with another ship and caused a fire on board the Mont Blanc, which led to a massive explosion that released nearly 3,000 tons of TNT. At the time, it was considered the largest man-made explosion, killing 2,000 people and destroying much of the city, uprooting trees and causing a tsunami. So, the belief has always been that to create bigger explosions, you need even larger amounts of explosives. This was true until the discovery of uranium and plutonium as fuel for bombs. Since the complete fission of 1 kg of uranium is equivalent to the explosion of about 17,000 tons of TNT. But in an atomic bomb, less than 1% of its nuclear fuel is converted into energy. And to create bigger explosions, like the Tsar Bomba, which was a nuclear fusion bomb that used plutonium, it was first necessary to trigger the explosion of a nuclear fission bomb in confined spaces inside the bomb to generate the heat and pressure needed to start the fusion of the plutonium. And so, the bomb exploded with a power of 57 megatons, or 57 million tons of TNT.